Okay, so in last part we discuss about the discovery of the electron and the palm pudding model. So in this part we will discuss the famous Rutherford Atomic Model, which is also called as nuclear model of Rutherford or the planetary model of atom. Okay, but it is well known as Rutherford Atomic Model. Let me say that Rutherford is also was a student of J.J. Thomson. So Rutherford first did an experiment, famous experiment. Also with Rutherford there are two persons who did this experiment. One was the Hans Geiger and another was Ernst Marsden. These three persons did this experiment around 1910, I guess. If I am not wrong, then this experiment was done in 1910, 1911. Okay, around 1911. So we should keep in mind that around 1905, Planck, Einstein did explain its photoelectric effect, and before that Planck also gave the quantization of light, these things. This concept was already known there, that means E equals to h nu, or the results of photoelectric effect. This was also very much familiar scientific community in that time. So after 5 or 6 years of photoelectric effect, this experiment was done by these three scientists, basically was guided by the Rutherford. That's why it's called the Rutherford Atomic Model. So what was the experiment? Rutherford took a alpha particle, source of alpha particle. What is the alpha particle? Okay, that was not known that time, what is the alpha particle or something, but at that time, at the end of the 19th century, the radioactivity was discovered. The existence of radioactive element was also known in that time very much, and that was known that the radioactive particles, radioactive elements basically emits alpha, beta and gamma particle, where alpha is a positively charged particle, beta was negatively charged particle, gamma is a neutral particle. This was known that time, around starting of 20th century it was known, and the radioactive elements were late elements after the lead, that means Pb, lead, radium, bismuth. So these were the very famous well known radioactive element that time. Marie Curie discovered the radium, and lead, bismuth, uranium. These elements are very well known radioactive elements. Okay, first Becquerel discovered the radioactivity. We know these things, I am not getting to that, but radioactive elements are very much well known elements, and the mass of the alpha particle, charge of the alpha particle, this was also known by the experiment. Scientists did not know the theoretical justification of radioactivity in that time, but experimental evidence was there. The mass of the beta particle, charge of the beta particle, because what was done, there was a magnetic field, right, and in the magnetic field the alpha, beta and gamma particles were traveling, and that was deflected in the magnetic field or the electric field. So from that experiment, I am not get into that, because the experimental setup I did not remember very correctly, but by using the electric field and a magnetic field, giving in the problem, I think there was some electric field in this direction and a magnetic field was inside the plane. This was the setup, and there was a Lorentz force acting on this total setup, and which guides the deflection of the particles. By using the Lorentz force and this deflection, we can calculate the mass and the charge of the particles. This was a basic setup. I am not going into the details how the mass and the charge of the particles were calculated. This was similar kind of setup used by J.J. Thomson to determine the mass of the electron and the charge of the electron, the discharge gas tube like setup. But here the electric field is also present, because we have to determine the charge. Now, okay, So we are considering that we are familiar with the radioactive elements. So this is a source of alpha particle, okay, and here let me draw it very clearly. This is called some beam splitter type setup. This is very thin, okay, narrow, okay, hole, and okay, if it's visible, this is the setup, okay, let me show it properly. So this is the setup, this is the source of alpha particle. It's difficult to draw, okay. This is the lead bricks, okay, lead bricks like this, and after that there is a gold plate, very thin gold plate, gold foil like this. This is a gold foil, so we are taking that. Let me draw it. So this is a very thin gold foil. It's very thin. It may be silver, but Rutherford did the experiment using the gold foil, and that there was a detector. Let me draw it. Okay, this is the detector. By using the detector, we can detect the presence of the alpha particle. So alpha particle was like this, and it is going to penetrate the gold foil. Let me draw. Let me give the data actually. Okay, this source of the element was bismuth 83214. This is a radioactive element. This is the radioactive element, and the alpha particle was, okay, the thickness of this foil, the thickness of the gold foil was 2.1 into 10 to the power minus 7 meter. So it was very thin foil. Why the very thin foil was taken? So that when the alpha particle was penetrating the gold foil, there must be one collision at a time. That's why if we consider the gold foil is made by lots of atom, as we are considering very thin foil, by which we can say that at a time this alpha particle will be interacting with only one atom at a time. So that's why this very thin foil was taken, and this spectrophotometer, I think, yes, this is the detector for ZNS, zinc sulfide screen. When alpha particle with this screen, the detector, okay, yes, the detector ZNS screen, zinc sulfide screen, then there will be some spot that by which we can say that the alpha particle is interacting in that point. Okay, so what was the observation? This was the experimental setup. ZN is basically a fluorescent screen, okay, which can interact with the alpha particle. So the observation was that most of the particle is going without any diffraction. That means it's going just straight. The angle is theta. The diffractive, that what is the angle? That means it is going like this, and after interacting with the gold foil, it was its previous trajectory. If it is diffracted like this, this is the theta diffraction angle. So most of the cases, most of the particle, the diffraction angle was 0 degree. That means it follows its previous trajectory after penetrating the gold foil. Very small amount of particle is deflecting with very small theta, very small amount of particle. we can say the data, actually the experimental observation, only about 0.14%, 0.14% of alpha particle, of incident alpha particles scattered by more than 1 degree. We should say the scattering angle is better to say. Okay, scattering angle. So more than, greater than 1 degree. So we can say that it's very small amount of alpha particle, incident alpha particle, which scattered more than 1 degree. So like this, and about 1 in 8,000. So we can compute the percentage also. 1 in 8,000 deflected by more than 90%. This was less than 90%, this deflection was, but very small amount was deflected like this, more than 90%. This was 1 in 8,000, and negligible amount of particle is deflected around 180 degree. You can say it's very rare particle which deflected around 180 degree, that means in this direction. So this was the result of this overall experimental setup. Okay, let me show the graphical result, then it will be more clear. So it was like this. Yes, the graphical result was, yes, this is the scattering angle theta, and this is the number of scattered alpha particle. Okay, how many numbers of alpha particles scattered in that angle theta? So it was, when it is 0 degree, around 0 degree, the value was around 10 to the power 10, we can say. This is like this. Oh. Yes. So this was the result. So you can say that when this is 100, let's say, if it is 100, then this is around 10 to the power 2. So we can say that this is greater than 90, but the number of alpha particles, scattered alpha particle, around also 10 to the power 2. So it's very much clear that if the scattering angle increases, the number of scattered particle also decreases exponentially, right? So the fraction is very less because the incident number of alpha particle was very huge, it's around 10 to the power 15, yes, around that. So this was the observation, but we have to interpret this observation. The observation, the interpretation of observation was following. Which is most important things: observations and inference. Okay. So what was the first observation? Most of the alpha particle pass straight through the metal foil without suffering any deflection. That means theta is 0 degree. Most of the alpha particle suffers no deflection, that passes as it is, following its previous trajectory. This observation said that most part of the space inside the atom is empty. Okay, that means 0 degree means theta is 0 degree means there is no interaction. If there is some kind of interaction of alpha particle with the elements of the atom, we don't know the elements of the atom, but according to the previous experiment, previous result, there should be electron and also some positive counterpart, positively charged particle. So if there is some interaction with the alpha particle which is also positively charged particle, then there should be some kind of deflection. As there is no deflection, that means the most of the particles feel no interaction with the elements. It essentially suggests that the inside, if we look into inside the atom, the most of the space is totally vacuum, totally empty space. That's why alpha particle passes as it is without any interaction. It passes, and it's around 99%, around, it's greater than 90 in fact. Okay, it's greater than 99% in fact. So you can say that the most of the part of inside the atom is empty. This was the first observation. Now what was the second? The low scattering angle. Okay, that means theta is around 1 degree, and we know that 0.14% of incident alpha particle scattered by around 1 degree. So what does it mean? It means that it deflected very less. 1 degree is very less amount. It means that, okay, we have to mind that the mass of the alpha particle, charge of the alpha particle is known. Also we know the mass and charge of the electron. So we can say that as the mass of the alpha particle is very greater than mass of the electron. We know this. Very much heavier element, alpha particle is very much heavier than the electron, and electron is negatively charged particle, alpha particle is positively charged particle. When it interacts, so it should be that alpha particle will be scattered very less amount, because electron is inside the atom, it will not scattered. Either electron may due to the collision, if collision is there, electron may be kicked out from the atom. That's a different thing, we are not discussing that thing. And the ZNS plate, the fluorescent plate, is detecting the alpha particle, not the electron. So that probability we are not taking care of. But now if alpha particle is scattered around due to the interaction with the electron, what will happen? That electron is very light compared to the alpha particle. So it is very clear that if electron is there and alpha particle is very heavier than electron, so when it will pass through electron, it will be scattered very less amount due to the mass of the electron, that is very light compared to the alpha particle. But there will be some kind of interaction because it's positively charged, it's negatively charged, electron is negatively charged. So this low scattering basically indicates the presence of electron. Okay, so now, and this was the due to the electrostatic interaction. So this is 7,000 times heavier alpha particle. Okay, so that's why the electrons are embedded discretely inside the atom. Now the third observation, large scattering angles. Okay, so this is very important. So large scattering angle, so it may be around 90 degree or maybe greater than 90 degree, it may be. So these large scattering angles, what does it signifies? We have to understand this. The alpha particle is getting scattered, that means by which it is getting scattered due to the interaction, it may be positively charged or negatively charged particle. So but due to this interaction, the alpha particle is scattered heavily, which readily suggests that the mass of that particle must be compared to the alpha particle. It should be a heavier element, heavier particle. That's why it make alpha particle scattered in a very large angle. So this is assumed to be nucleus, presence of the positive charge particle. Okay, so it may be greater than 90 degree also. Rutherford basically argued that to deflect the alpha particle backwards, also in some cases theta is 180 degree. That means, as I discussed here, some is also 180 degree. So when it will possible for the scattering of the order of greater than 90 degree or even 180 degree, though it's very rare, As I mentioned before, these scatterings are very rare, and this is almost negligible, but it's happening na. It's maybe rare, it's 1 in 8,000 this scattering are, and in 180 degrees is more rarest event, but though it's happening, when it will happen, when the scattering will be around 180 degree, for that scattering Rutherford said that it must experience, the alpha particle must experience a large repulsive force, which otherwise the alpha particle will not be scattered in the 180 degree, because alpha particle is much heavier element, a heavier particle, so it's scattered around 180 degree, which essentially suggests that the entire positive charge of the atom, because it is confirmed that there is some positive charge, otherwise the overall charge will be not neutral. There should be some positive charge which can balance the negative charged electron. So the positive charge, almost total positively charged, and the mass of the atom was concentrated in the small space of the atom, which was called as nucleus. So it is actually the positive charge, and it has almost the mass of the atom is concentrated in the nucleus. So we will discuss further, we will carry forward from here. So let me stop in this part here. So thank you.